All right, so here we are in Chapter 7, Foundations of Math 10. We're in Chapter 7. I'm going to attempt a bit of a combined 7.1, 7.2 lesson today. So we're going to talk about systems of linear equations, which is a very important concept that's going to come up all throughout math now, in your future math classes. It can be very important. As a matter of fact, with the Pre-Cal 20 class just yesterday, we talked about systems of equations, and I referred back to what they learned in grade 10. So they're doing systems of other equations, not just linear. You guys are starting with systems of linear equations. And 7.2 is solving systems of linear equations graphically. So we are going to graph the linear equations that are involved in the system, and we're going to find out where the solutions are once we graph. So that's the goal today. And so, first of all, what is a system? A system of equations is basically it's more than one equation that is considered together, okay, to form a system. The body system, okay, the skeletal system is like all of your bones, right? Digestive system, right, from your mouth to your tongue, your throat, your stomach, your intestines. It's separate parts working together. So in math, a system of equations would be multiple equations working together. Now, a system of linear equations would be more than one linear equation working together to solve some problem. So we have two parts here. We have, we have systems, more than one equation, and in your case, we're going to be dealing with two only, okay? And linear is straight lines, so straight line relationships. So we're going to have two straight line, that's linear, functions. Really, they're all going to be functions working together. Okay, two straight line functions that are going to work together to help us solve a larger problem. So, not every problem can be solved with a system or represented with a system of equations, but I'm going to read through the first example here, and I'm going to talk to you about how there are two distinct parts, two distinct different kinds of relationships that can work together to solve this problem. So this is a good example. So a school district has buses that carry 12 passengers and buses that carry 24 passengers. So they're big buses and small little buses. The total passenger capacity is 780. The total passenger capacity is 780. So that means that 780 kids can fit on the number of buses, large and small, that we have. Here's another bit of information. There are 20 more small buses than large buses. Okay? Now, we haven't asked a question here yet. Okay? We haven't asked a question. What we're trying to start with here is how to represent the equations that are involved here. Okay? So how can we get two equations out of this information? All right? Two equations out of this information. So some things we want to consider are this. We need some variables, okay? So we need some variables to make our equations, right? And so you have to ask yourself, what are the variables, what are two variables that we can use, and what would they represent? Okay, so usually there's two variables, okay? So we have 12 passenger buses and we have 24 passenger buses, all right? The total passenger capacity is 780, all right? So we have buses and then we have students that go on the buses, okay? And then there are 20 more buses, small buses than large buses, okay? So what are two things that we are considering in this question? Where do we want to start? What are some ideas?
Maybe the amount of each type of bus?
The amount of each type of bus, meaning what? What do you mean?
Be like, there could be like X amount of 12 passenger buses and...
Okay, so the number of large buses and the number of small buses. Yeah. Okay, that's good. Okay, that's good. Any other ideas? Okay, do we want to consider students? Like, should S be students maybe?
No.
Well, no, because you have a reason?
Because it is definitely like 780. There's a specific quantity there.
Okay, so I like that thinking. The total passenger capacity is 780. So if we let S equal a variable that we don't know, well, it looks like we do know what S is. So that's not a variable that's unknown, right? So really, these should be unknown variables. We should qualify this and say unknown variables. What would they be? And I kind of like what's been suggested here so far, that maybe L, let's do L equal large buses. Okay, then specifically the number of large buses, let's say L, and let's use capital L. So the number of large buses. And let's do S, capital S, is the number of small buses. Okay? All right, so you're jotting all this down. You're jotting all this down. Write all this down. Okay? You want to have a record of all this, okay? Because you're going to have to refer back to these examples to figure out sort of like, hey, what did I do there? Why did I not write S for students? Oh yeah, students was given. The number of students is given. That's not an unknown variable. That's actually known. So I don't want to waste a variable on something that I already know. Okay, so if we do that, let's start with this. Let's see if we can make two separate equations here. And I'm going to highlight this for you. The first sentence, okay, is this right here. So we know that we have two different kinds of buses. That's taken care of with identifying our quantities. Awesome. The second sentence, the total passenger capacity is 780. Okay. And so the number of students on an unknown number of large buses plus the number of students on an unknown number of small buses has to equal 780. Okay, now I'm going to go one step further and highlight the third sentence, because this actually is the easiest one to start with. There are 20 more small buses than large buses. I think the easier equation to start with is that last sentence. The last sentence gives us some information on one of the equations. There are 20 more small buses than large buses. If I wanted to make an equation, something equals something else, how could I use these variables and this last sentence to create our first equation? Any ideas? How do I represent an equation with that information? Go ahead.
S equals L plus 20.
So S equals L plus 20 is your guess. Okay, let's write that down and we'll just see if that makes sense. S equals L plus 20. So in an equation, this says that the number of small buses is equal to the number of large buses plus 20. And it says here there are 20 more small buses than large buses. So in order for them to be equal, I would have to add to the smaller side. So L is smaller, right? The number of L is smaller, so to add 20 to make them equal makes perfect sense. Yes. That's correct. Now, don't be tempted to just say, oh, 20 plus S equals L, because that's the way it's written. No, 20 plus S equals L. That means that the L is small buses plus 20 more, which is exact opposite of what it said. So the number of small buses is more, so we have to add to the fewer number of buses. Does that make sense? Everybody good with that? Now, you also could have written this. S minus 20 equals L. That's okay too, because there's more smaller buses, there's more smaller buses, so if we subtract 20 from the number of smaller buses, we'll get the number of large buses. Does everyone see that? You could have done that as well. Either one are acceptable. I usually tend towards an equation that has adding instead of subtracting, but that's just personal taste if you have a choice. If I have a choice, that's what I end up doing. Okay, adding instead of subtracting, but it doesn't matter. Okay, let's go back to this one, because this is the tougher one. I think this is the tougher one. So how do I get an equation out of those two sentences right there? How do I get my second equation? It has to have something to do with capacity, right? Number of students. So what do you think? What do you think? This one has to include like students involved here somewhere. This is just number of buses, right? That's just number of buses. This one has to include students somehow. and I'll give you a hint, it has to equal 780. So how do I get the buses, our variables, this idea, how do I make the left side of this equation? Any ideas? Okay, so S is the small bus. What makes it a small bus?
It's less people.
Has less people? How many people can fit on each small bus? 12. So if I have a certain number of small buses, the number of people that will fit on small buses would be 12 times S. 12 for every S. So guess what? I'm going to write 12 S, because this is passengers on small buses, plus, what's going to be the second half here? 24 L. Now don't have to do L plus 20. We're just talking about the large buses. Okay? So this is a great second equation here. Okay? That's perfect second equation. Now, you want to check when you do your equations. This is number of students, right? Number of students. This represents a number of students. That's good. And this represents a number of students. That's excellent. So you want to make sure within an equation that they align. What about up here? Well, that's a number of buses. Number of buses. This is a number of buses. And this is a number of buses, right? Small buses, large buses, and 20 more buses. So does that make sense? The first equation is about buses, number of buses. Second equation is really about the students. And what we're learning in this section is how to take the information from a question and make two equations. Okay? Now we're going to come back and maybe make a question and find out what can we find out here with this? Any ideas? Like, what are the unknown variables? L and S. So a question would be, how many large buses and how many small buses are involved here, right? That would be an obvious question we could answer here. But I'm going to pause there, and I'm just going to move to the next sort of question to create another system. Okay, so this is question number 1. All right, I think I have question number 2 up here. Oh yeah, so this is from your textbook here, and this is talking about dimensions of a flag. Okay, the Nunavut provincial flag appears to be. So let's read here. What does this say? The question says, create a linear system. Okay, so that's going to be 2 equations to model this situation. Here's the situation. The perimeter of the Nunavut flag is 16 feet. Okay, that's bit of information number 1. Bit of information number 2, the length is 2 feet longer than the width. That's information number 2. And we're going to be able to make 2 equations from these 2 distinct bits of information. Okay, so we're going to forget about B for now. Let's do A first. So create a linear system. I have a picture of the flag here for you. And I've noted that the width is going to be, I'm going to put the width on the side, the length on the top and bottom. What? That should be length. Okay. And so what's the equation I can build for this first part here? What's the first number 1 equation going to be? Number 1 down here. Sorry? Okay, P is equal to 16. Okay. P is equal to 16. Now, what I want to do, remember what we did first of all, is we identified, hey, what are the variables? What are the unknown variables involved, right? Unknown variables. So that's going to be length, okay, and width. So if you say P equals 16, we're not including any of our variables that we're going to involve in the question. So a good place to start, yeah, P is 16, but how can we make an equation that involves W and L in this equation? How can we turn this into an equation that has W and L in it?
2W plus 2L equals 16.
Okay, the perimeter is the distance all the way around, which includes length plus width plus length plus width. So 2 lengths, right on, plus 2 widths equals 16. That's perfect. And obviously you can start by thinking, hey, the perimeter is 16, so what can I do with that? How can I make an equation with 2 unknown variables? And sometimes it's just with 1 unknown variable, but this one would have 2 unknown variables involved, the length and the width. We good? Now we can't assume that it's a square and just have L, or just have 1 variable. We can't assume that. It's length plus width plus length plus width. Now it might end up to be the same. It might end up to be a square. I don't think it is, but it might end up to be a square. Let's look at the second bit of information. Oh, here we know it can't be a square. Okay. Why? Because the length is 2 feet longer than its width. So remember, the length is the long side. So I am going to start by saying the length, being the long side, is equal to what? Someone help me finish this equation, just like we did the last one with the number of buses. Okay, wait a minute. You said 2W plus 2. Okay.
Or 4.
So the length itself, like 1L, is 2 feet longer than 1W. So you're close. This would be just W plus 2. Does that make sense? All right. Perfect. That's perfect. So this is equation number 2. All right. So that's half the work right there. Well, maybe a little less than half, but pretty close. 40% of the work right there of the question. It's like coming up with the 2 equations, because sometimes it's easy, sometimes it's not. But those are 2 prime examples of what you're going to be faced with here as you work on this kind of stuff. Okay, so let's do B. Denise has determined that the Nunavut flag is 5 feet long and 3 feet wide. Use the linear system from part A to verify Denise's findings, to verify that she's correct. So we're not actually solving for L and W here yet. We are just verifying some possible solutions, okay? So does it make sense? Okay, so is L equal to 5 and W equal to 3? Well, if that were the case, then these values of 5 and 3 should satisfy each equation. And by satisfying the equation, what I mean is that when you plug those values in, the left side should equal the right side. It should be an equation. Everything should line up. So let's test. Let's test. Okay? So B, I'm going to try 5 and 3 in the first equation. 2 times 5 plus 2 times 3 should equal 16. Let's see. 10 plus 6 equals 16. That is true. So that works for the perimeter. Does it work for the length and the width relationship? Well, this one's going to be pretty easy. Is 5 equal to 3 plus 2? Yes, it is. So if you insert the values into the equations that you've made, the 2 equations, and if they satisfy the equations, you got the right answers. Any questions there? Creating equations, verifying possible solutions. Okay, so our third example here, this is example 2 in your textbook. It's on page 398 in your Foundations and Pre-Calculus Mathematics 10 by Pearson Publishers. So page 398, it says this. Create a linear system to model this situation. That's what we're going to focus on here. And then we'll talk about maybe solving it next. So create a linear system. In Calgary, a school raised $195 by collecting 3,000 items for collection. Okay. All right. So raised $195 by collecting 3,000 items. Now, this question, you can't take the first sentence and make an equation, the second sentence make an equation necessarily. They've mixed things up a little bit. But you're smart enough to know that one equation is going to deal with money, because you've got money here, and another equation is going to deal with the number of items, because that's what we've done before. So $195 is going to come from the money that you get for each of these things. So I'm going to skip over to here and to say that the money involved, 5 cents for each pop can, and 20 cents for each large plastic bottle. So those go together. The total money comes from the money from this plus the money from this. That make sense? So we have a money equation. All right, so this one's a bit mixed up here. But the second part is this. They collected 3,000 items for recycling. So 3,000 total objects. So we're going to make an equation. All right, equation 1, I'll do it in blue. Equation 1 is a money equation. Money equation number 1. So that one is going to be a total of $195. And what does that come from? It comes from turning in the pop cans and the large plastic bottles. Okay, all right, well, pause. Maybe we should take some time to identify our variables, right? We always have to do that. I kind of speed by that because it is a step we have to consider, but sometimes it's pretty obvious, but I'll pause here. So what are the unknown variables in this problem? They are, yeah, number of pop cans and number of large bottles. So let's make P equal the number of pop cans, okay? And let's make B equal the number of the bottles, okay? All right, so that's going to be pretty important to identify our variables, okay? Our unknown variables. So the money comes from, now this is dollars, right? So the number of pop cans, I have to be careful here as well, that I can't put just 5 here, right? Because this is dollars, this is dollars. This has to be dollars as well. So is it $5 per pop can? Nope. It is actually, yeah, wish, eh? It's actually $0.05 per pop can. So another thing that we want to learn here when building our equations is that the units have to agree throughout the equation as well. So we're dealing with money plus money equals money. Okay, that's a money equation. But you also have to have your units have to align. So dollars, dollars, dollars. Can't be cents, cents, dollars. Not in one equation. They have to be consistent. So what am I going to write for this next part then? I get 20 cents for the bottles. So the number of bottles times 20 cents. How do I write 20 cents? 0.2, right. And if you want to 0.20 for 20, that's totally fine too. Okay? All right, that's equation number 1 with the money. And I think that this is the toughest equation to get. The other one's pretty easy. But this is the tough one. And if you could remember that within your equations, each little piece has to have the same units and has to be talking about the same thing, then it's going to be easier. Okay? Remember, you can't mix up cents plus cents equals dollars. You could change the dollars to cents if you want. You could 19500 cents. And then you'd have 5p plus 20b equals 19500. And you could do all cents. That's fine. Usually we just do dollars. Okay? So the next one in yellow here, I'm going to do equation 2. This is going to be just number of items, right? So this one's really easy. There's 3,000 total items. So P plus B equals 3,000. Done. Easy. So we have number of items plus number of items equals number of items. You okay with that? Yep. Good? Okay, so we got a money, we got a number of items. A lot of times it's something values and just number of items. There's usually one equation that's pretty easy just like this. Okay, almost always. And another one has to do with some other kind of quantity. Okay. Now the school received 2,700 pop cans and 300 plastic bottles. Use the linear system to verify these numbers. So 2,700p and 300b. Okay, let's see if does that equal 3,000? 2,700 plus 300, that equals 3,000. Okay, and then we could do some quick math on a calculator. I don't think we'll do it here now, but you could do 2,700 times 0.05 plus 300 times 0.2, and that should equal 195. Okay, in your textbook, as part of the solutions there. They will do it somewhere. Okay. And you can look at there and see what that we've done the same as the textbook looks like. Okay, everybody good with that? All right. Now solving. Okay, let's. I'm going to take the next half of this class here. We're gonna push into 10.10. Oh wow, 7.2. I did chapter 10 in calculus last period, so 7.2. Now 7.2 is solving a system by graphing. So first, let's talk about what solving means. Okay, so this is that was 10.1. Let's take a look at 10.2. That was 7.1. Let's look at 7.2. Thank you. Seriously, we're not in calculus. Okay, so solving a system of equations. Okay. That's what we're going to do. And we're going to do this graphically. And we're going to save algebraically for a little bit later. Okay? We're going to solve graphically. That's 7.2. And we're going to get into this. We're going to work with those 3 examples that we did, and I'm going to show you how we're going to solve graphically. First of all, what does solving mean? Solving. Okay. If we want to solve a system of equations, it means that we want to at least, the most basic is, find the values for the unknown variables, okay? So those variables that we set, we want to find the values for the unknown variables given the equations, okay? So solving means finding the missing values. So find missing, that is the unknown values for the variables. Okay? That's what solving is, right here. Find the missing or the unknown values for the variables. And trust me, you're going to, throughout math here now, okay? The rest of your 10th grade year here, grade 11, grade 12, calculus, foundations, whatever you end up taking, they're going to have solve, okay? Solve this equation. You need to find the missing values. That's what solve is. There's something that's unknown, that we don't know about, so you need to solve the answer, solve for the unknown variable. It sounds very straightforward and easy, but trust me, there are grade 11s and grade 12 students that I say solve this equation, they're like, oh, do you want me to graph it? Oh, do you want me to, what do you want me to do? So, also solving triangles. How do you solve a triangle? You find the missing parts, angles, sides, you solve, okay? Solve is finding the missing values. All right, so graphically means we are going to literally graph the 2 lines and find out where they cross each other. The fancy word is intersect, where they intersect. Okay? So solving the system of equations graphically, what do you mean graphically? Well, graphically, down here, graph each equation and determine intersection point. Graph each equation and determine the intersection point. Because let's face it, the x and y unknown variables in one equation, if they're the same for both, guess what? That's the exact same point on both lines. Where is the exact same point on both lines? Well, it's at the exact point they intersect. So if we are looking for values for the variables that fit 2 equations at once, that means we're looking for the intersection point of 2 graphs at once. Somebody grab that door there. I'm hearing pumping music coming in from the hallway there. It's a little distracting. Okay? So we simply graph each equation, find the intersection point. Awesome. Okay. I'm going to now go back. Which one? Okay. These are pretty big numbers. I'm not going to graph those ones. Let's start with this one. Let's start with this Nunavut flag. Now, I know what the answer is, but guess what? I am going to copy these equations. So we're going to use these 2 equations, so you might want to just re-copy these down real quick. Okay, we're going to graph this Where am I going? Come on now. Here we go. Oh my, I gotta make some space here. Draw, insert space. Okay. 7.1, really? Oh yeah, okay, here's 7.2, right. We're doing a combined lesson, so this is 7.1 and 7.2. Big space, okay. View, back to 100%. And apparently I'm shifted over just a little bit. Okay, for whatever reason that is. Okay, so here they are again. There's my two equations that I'm gonna start off with. Okay, so example 1. Or whatever example this is, example 1 for this 7.2 part. Okay, so I'm going to graph each equation and determine the intersection point. All right, let's see if you have graph paper, good for you. That's going to be helpful. If you don't have graph paper, just make your lines, your tick marks the exact same as best you can, the same distance apart. But it would be best with graph paper. Okay, now here's the thing, guys. Here's the thing. We've normally been graphing X and Y. We don't have X and Y, we have W and L. No big deal. You just have to pick one to be on the horizontal axis and one to be on the vertical. If it makes sense that one is the independent variable and one is the dependent variable, then great. In this case, we have length and width of a flag. So one is really not more important than the other or more dependent on the other. So let's say length here, okay, and width here. It doesn't really matter which one's which, really. Okay? Or actually, now that I look at it, it does matter. Actually, sorry, change that. Do length here. Why? Because this is like Y, you see? And this is like X, see? So it's already set up that way. So let's do it this way, because we already have like a Y and like an X, and this is a very familiar linear equation right here, isn't it? Y equals X plus 2. That's easy to graph. So that's why I'm gonna do that, just because I've got this set up already. So Y equals X plus 2, or L equals W plus 2. So I'm gonna take 2 here as my B value, my y-intercept. And what's the slope? 1. So I'm going to go up 1 over 1, or I'm going to go up, I don't know, I'm going to go up 8. I'm going to go up 8 to 10 here. I'm going to go up 8 and over 8. Why not? Just going to pick a large number. Up 8 and over 8. Somewhere around here. Your graph paper will be much better than my no graph paper. Okay? Now, should I extend this graph all the way to the left here as well? What do you think?
Yes.
For the context of this problem, okay, I see some heads nodding and some heads shaking. Okay, why would I not extend this graph to the left any further here? Why would I not do that? Is there an argument for not doing that?
How do you have a negative length?
Width or length of a
Okay. The length can be very small, can technically be 0. It's not much of a flag, but it can be very small, but it can be negative. So we can't have a negative distance. So right, this graph right here, you probably wouldn't bother with anything that's negative, okay? Only keep it positive, okay? All right, everybody see this? Now let's graph the other one simultaneously. I'll graph this one in blue maybe. So this one is red and this one is blue, okay. So 2L plus 2W equals 16. How, right? Well, in order to graph this, you could change this around and solve for L, or you could use a table of values. I want to show you how to do this because, honestly, it seems that a lot of students, for some reason or another, don't like using tables of values. So I'm going to use W as the kind of the X, as we've got it down here, and L as the Y, right? So a table of values, let's start with 0 on W. If 0 is W is 0, then this is 0, and I have 2L equals 16. What is L?
8.
8. Does everybody see that? If W is 0, L is 8. 2 times 8 is 16. Okay. What about if W is 2? What's 2 times 2? That becomes 4. So 2 times something plus 4 equals 16. Well, if you want to show your work down here, I appreciate that you can. So 2 times L has to equal 16 minus 4, or 2 times L has to equal 12. So L is 6. Okay. What about 4? Okay, what about 4? So 2 times 4 is 8. So L is going to be 2 times something plus 8 is 16. So 2 times L has to be 8. L has to be 4. Okay. All right. Is that all we need to graph? I mean, we got 3 points, so I guess we could graph that, right? So let's go 0, 8. And again, I apologize. Mine's not going to be that great because I've got no graph paper. I know, monkey see, monkey do. Do as I say, not as I do. 2, 6. So we're 2. 2, 6 will be about here. 4, 4. Yeesh. 4, 4 is about here. Okay. Now, so 8, 0 actually is going to be a point too, right? 8, 0. So if W is 8, 2 times 8 is 16. So what plus 16 equals 16? That's 0. So here we go. There is a point down here. So if we are connecting these values here, so you should see that this intersection point, where does this intersection point lie on your graph? What point is this right here for you on your graph?
2 and 6.
What is it?
2 and 6.
2 and 6. Okay, 2 and 6. You were going to say something else? 3, comma 5. Okay. What about somebody else? Help us break the tie here. You have 3, 5?
Wait, for what?
3, 5? What's the intersection point here? Okay. So it looks like 3, 5 is our intersection point. Okay. Now, that's what it should be. 1, 2, 3, up 5 is 3, 5. Now, double check your line there. Okay. But notice what 3, 5 represents in this equation. It's the intersection point. It means W is 3 and L is 5 for the blue line. It also means that W is 3 and L is 5 for the red line. And when we're talking about a solution for a system, we want to look for numbers that satisfy both equations. So the numbers that satisfy both equations are the intersection point values. So width is 3, length is 5. The flag, in this case, is 3 by 5. But none of it flagged there, okay? However that flag looked. Okay, got it? So solving by graphing, what do? We graph it. What do you mean graph it?
Graph the equations.
Graph each of the equations separately. And then you look for what? What do you look for? The x-intercepts or the y-intercepts? Where they touch the x and y axis? Are these the solutions right here? No.
The lines intersect.
We look for this intersection point. There will be one point of intersection that will give you the values for your independent variable and your dependent variable, and that's what you're looking for. Okay. All right, this is going good so far. I am going to show you, boy, should I show you how to use the graphing calculators to do this? I think I should. I think we will. I think we will. Let's use the graphing calculators to do this one, because this one's got decimals. Ooh, tough. Yeah, that's tough. So let's use the graphing calculators. Have we learned how to graph with the graphing calculators yet with you guys?
Yes.
We did a little work with them, didn't we? Okay. All right. Let's do this one. You guys should be happy. I don't know why you sad. The graphic calculator is going to save you a bunch of work. You should be happy. Yes, technology. Come on, you're kids. Don't you like technology?
I don't like technology.
Oh, boo.
He types like this with his 2-pointer finger.
That's not how I
Oh, so fine.
This line is a graph.
Okay. Write that down. Find P and B. Write those two down. We're gonna using the graphing calculators. All right. So each of you have a graphing calculator. We've done this before, so we are going to go to y equals. Remember y equals? You're gonna clear whatever you have on there. Clear it. Make sure your plots are not highlighted. You are going to type in the equations. Now, the only problem is that in the graphing calculators, you have to rearrange the equations so that you have y equals something in x. So guess what? We're going to have to pick which is x and which is y. And we're going to have to do a little bit of rearranging first. So what do you think? Let's do P down here and B here. So P is our X, B is our Y. So let's solve for B, okay? In the blue graph, we have to do a little bit of work here first. So 0.20B equals 195 minus 0.05P. Now to get B by itself, I divide everything by 0.2, right? So that's going to be B equals, you can do this on your calculator. You might have to just pause and quit that. So 195 divided by 0.2 is 975. Is that right? Times 10 divided by 2, yep. 975 minus 0.05 divided by 0.2 is 0.25. So we have to take our equations and we have to solve for our dependent variable. So let me know if this is correct. Did I hear someone say I'm so confused? Did I hear those words? I'm solving for this variable
Yeah.
right here.
Oh,
But
you're
what am I
isolating.
putting?
Take this over.
No, he's
Okay, well, we're just isolating the variable first.
Oh,
So now this is like the y. This is like the x. So go to y equals, type in 975 minus 0.25 x. Okay, your calculator does not have every conceivable variable on the button. It just has x and a few others. So this is what this should look like. Questions there? Okay. Now, if you want to let things equal x and y in your problems, then go ahead. But it's better to let your unknown variables equal letters that represent what they're representing. Question? Do you have a question?
Why does it change to P after you take it over?
What changed to
Why
P?
does
No, no.
25 change?
No, this. So this comes from this right here, right? So I had to do 0.05p divided by 0.2, and that became 0.25.
Okay.
That make sense?
Yeah.
Yeah. Okay. All right, so do the same thing for the other one. So in yellow, this is going to be easy. This is going to be B equals 3,000 minus P. And so that's going to be, in the next line, 3,000 minus your variable. Okay? Okay, now this has some pretty large numbers too, so our window is going to be a little bit wacko. Okay? All right, but let's do this. Everybody zoom 6, and then it will graph those lines. Now the problem is you're not going to see anything like that, are you?
Yeah, I don't see anything.
Okay. So you haven't done anything wrong. We just have to adjust the window settings. So on your calculator, you could do one of two things. You could zoom out, but if you keep zooming out, everything is going to get super small and it's not going to work. So instead, what you should do is you should use your head a little bit and think, okay, what are my y-intercepts here? Almost 1,000 and 3,000, right? So what you're going to do is you're going to extend your y maximum. So hit the window button here, window. Look at where it says y max. You see how y max is 10? We need to make that like over 3,000. Let's do 3,500. Okay. Now, how many pop bottles are we going to need? Well, we know what the answers are to this. Didn't we verify the answers? 2,700, right? Something like that. Okay. Well, and 300 or something. So guess what? The X max is probably going to have to go bigger too. All right. So let's make that 500 or something. Just start with that. So I'm making the y-axis larger on top and the x-axis larger on the right. So this is what I have. This is what it looks like now. So those two lines are there, but I still don't see an intersection point. Do you see that? But it looks like, the way this is trending, that the intersection point is going to be way over here somewhere. So I need to make my x-axis quite a bit larger. So let's go ahead and do that. Go back to the window setting. X maximum. I should make that like 3,000 or something. Make it really big and then see what happens. Ooh, that looks good. Oh, yes, yes. So you might have to adjust your window settings for each problem to find an intersection point. So guess what? I need to find out what this intersection point is, and then I'm going to find my solutions. Okay? Now, have we done finding intersection point yet with you guys? Yes, no? Okay, let's do it quick in the last few minutes here. So second function trace is the calculate. You see that's a second function there, calculate menu. This is super important. Super important menu, calculate menu. Notice that option number 5 is intersect. So let's hit number 5, and it will pop back to your graph screen. Okay. So you have to tell the calculator which two lines that you want to find the intersection point for. Now, we only have 2 lines graphed, but the calculator is still going to ask the question. It says first curve right here, and you're going to say yes by hitting enter. Then it's going to pop up and show you in the top left the second curve, and it's going to say, hey, is this the second one you want me to consider? You hit enter again. So it's just enter, enter. Now, because there's only one intersection on the screen, the calculator says, do you want me to guess the intersection point now? You hit yes. And it should go right over to the intersection point and give you the values right there.
Wait, are we going to get to use graphing calculators on our final?
You will get to use graphing calculators on evaluations when and where you need to. So there may be, I don't know about that. I can't answer that question yet. So if yes, then there will be portions of the exam where you will be given a calculator, probably not all the exam, because there's much in this course that you should not have a calculator for, because you'll have to know characteristics of different graphs without plotting them. So if you need a calculator, you'll be given a calculator. Let's just put it that way. Okay, quickly, we got to end, guys, quickly, before the bell rings here. Now, notice that x is 2700. Well, what did we let x equal? X was the p. So p is 2700. And y is the b, so b is 300. So guess what? We will verify this. Don't have time right now, but you plug those values into each of the original equations. Check to make sure that they satisfy the equations. And then you always end with a final sentence. So there are 2,700 pop cans and 300 pop bottles. And circle your answer, please, showing all your work. Okay? So please put your covers back on your graphing calculators and return them to the bin up here. I will show you your homework in a second. So 7.1, 7.2 homework you should be able to do now. And I will give you some class time to work on that with the calculators another day. Again, MrMathWell.com, go there for all of your math science needs. There they are. All right, dismissed.
Why are you pressed?
Tired? Yep, you should get some sleep. Get some sleep at night. Good idea.
It wasn't.